Okay, so we have a lot of knowledge. We know what things happen, where things happen, why things happen, but most of our knowledge is really represented in our language, and it's not always clear what we mean when we say things. And so I want to talk about these ontology logs, which are ways which we can take our everyday kind of knowledge and embed it in pure mathematics, represent it in category theory. So this is a fantastically powerful idea. So I'm just going to jump right in with this example. We have these objects here, and these represent abstract concepts. For example, a planet, okay? And it's really best to think of these as representing sets. So when I say a planet, I really mean a kind of generic member of the set of planets, okay? And these arrows here are representing aspects. So an aspect of something is a way that thing may be regarded or measured. So we can say a planet is a celestial body, and that makes sense in plain English by virtue of the fact that we kind of label these objects with these indefinite noun phrases. But there's more going on than just specifying English sentences, because we can look a bit deeper at this. When we say a planet is a celestial body, what we really mean is that there's a function called is, which is sending every planet to a celestial body. Okay, so this is a really deep idea, and I think it's a really nice one because, I mean, the sentence, a planet is a celestial body, may seem kind of clueless, but when you think that that's actually specifying this kind of function, so you've got the set of all planets in the universe and the set of all celestial bodies in the universe, and you're drawing arrows from planets to celestial bodies, that seems like a much richer kind of notion, but this is just kind of revealing the sort of hidden beauty of our everyday language, I think. Anyhow, the basic idea behind these ontology logs is that we have these objects here, which are basically representing sets, and we have these arrows here, which are basically representing functions. But these ontology logs are written using these indefinite noun phrases for the objects and these kind of descriptions of these functional relationships on these arrows. And that means that we can also read these ontology logs in terms of plain English. That makes these ontology logs more kind of expressive, more accessible. So there's two more really important things about these ontology logs. One of them is that we can compose these arrows together. So we can do this kind of linguistically just by adding words like which in the middle. So a planet is a celestial body, which is a trajectory. That's a coherent sentence, but it's more than that. It's actually making a functional relationship. So when we say is a celestial body which has, we can think of that as a sort of function which sends every planet to a trajectory. So if we get a planet, that is a celestial body which has a trajectory. So somehow this is specifying a kind of function from the set of all planets to the set of all trajectories. So this is one of the big ideas. The other big idea is the idea that some of these paths might be equal to each other. In other words, some of these paths might commute. So we say paths commute when, if we compose all of the arrows along those paths, those end up giving equal kind of functions or equal kind of arrows, more generally in category theory. Okay, so we'll denote commuting paths using a kind of green loop like this. And that means that the paths around this region are going to commute. They're going to compose to give the same results. So what this means in this case is that a planet is a celestial body which has a trajectory. That's going to be some trajectory in here, and that'll be the same trajectory that we get if we go along the arrows this way. So a planet has an elliptical orbit around a star, which is a trajectory. That's going to refer to the same trajectory. Hence, composing this arrow with this arrow equals what we get if we compose this arrow with this arrow. So now we understand what this means at a kind of deeper level. We see it not only makes sense in English, but it's defining these kind of functional relationships. But we can go deeper still. I mean, what I'm trying to do here with this diagram, with this ontology log, is give a definition of what a planet is. So I looked in a dictionary and it said a planet is a celestial body which has an elliptical orbit around a star. Okay, so I thought, how can I represent that in category theory? And this is what I came up with. So I think this is a true ontology log, but I think it's more than that. It's actually reflecting this definition of a planet. And that's because this ontology log was created using a special kind of piece of machinery from category theory. And this is the idea of something called a pullback, okay? So I want to tell you about these pullbacks. My basic goal in today's video is to give you enough tools to be able to make ontology logs yourself about subjects you're interested in. So I think this is a really brilliant thing to do because number one, when you do this, when you try and represent something you know using an ontology log, it really kind of forces you to think about things in a very kind of clear way and to organize how all these concepts are related to each other. And usually you get a very kind of different viewpoint on your subject because somehow you're able to represent everything so that all of these kind of arrows, these connections between concepts, really represent functions. So there's a whole lot of information there. Okay, so the important kind of category theory idea behind this ontology log here is the idea of a pullback. So a pullback is a kind of limit in category theory. When we're working in the category of sets, as we are here, where we have objects representing sets and arrows representing functions, the definition of a pullback is pretty simple. And I give the definition here. Okay, so suppose we have a set A and a set B and a set C. Now, because we're using ontology logs, I'll talk about this set A like this. I'll say a member of A. And then let's say we have a function f that sends members of A to members of this set C. So normally we'd just say we have a function f from set A to set C. And also, suppose that we have a function g from this set B to this set C. Okay, so if we have this stuff, we have sets A, B, and C, and we have this function f from A to C and this function g from B to C. That means we've basically got this part of the kind of diagram here specified. And then we can ask, what is a pullback of this? Okay, so what's a pullback of this kind of part of our ontology log, these three objects and these two arrows? And essentially the answer is this. It's a set of pairs, and these pairs have their first entry from this set A and their second entry from this set B, and they have the feature that if we do this function here f on the first entry of the set, then we get the same answer in C as we do if we do this function g here on the second entry of our pair. So this is an enormously powerful idea because it allows us to kind of form a new set which is made by kind of combining elements of this set and elements of this set in such a way that they have common features. Now, there's actually a little bit more to a pullback than just this object. We also get these projection functions here, which basically allow us to kind of extract these pieces from these pairs. So we have one of these functions I call little a, and that just takes the first entry of one of these pairs. And the second function I call little b, that just takes the second entry. And so now we know what pullbacks are, okay? They're basically this set of pairs such that if we do F on the first entry of the pair, we get the same answer as if we do G on the second entry in the pair. But how does this diagram here correspond with this diagram here? Well, basically, if we just think of capital A as the set of celestial bodies and capital B as the set of elliptical orbits around a star, and capital C as the set of trajectories, and F as has and G as is, then you'll see that these two kind of diagrams look very similar. So all I've done here is just rewrite this kind of pullback object in this sort of more mathematical language. Okay, so instead of saying a planet here, I'm now saying this is a pair, C comma E, where C is a celestial body and E is an elliptical orbit around a star, and the celestial body has the same trajectory as the elliptical orbit around the star is. Okay, so hopefully you can see that this just corresponds to this kind of form. Okay, so let's go deeper into this seemingly kind of trivial definition of a planet. So now we can ask, well, what does this mean? What's it mean to have an elliptical orbit around a star? And I was thinking about this for a while, and I don't think it's actually as simple as it sounds. I mean, okay, we know what an elliptical orbit is, and let's suppose we know what a star is, but what does it mean for an elliptical orbit to go around a star? I mean, we have an ellipse, and where's the star allowed to be in order for this statement to be considered true? And so when you start thinking about this and how you can make ontology logs, you start thinking, well, I need to have functions. And so functions really should be precisely defined. And how can I precisely define what this means? And so, I mean, really, it came back to Kepler's law. So Kepler was an astronomer who made these different laws of astronomy, and his first law is that a planet moves in an orbit which is an ellipse, and an ellipse has two special points called focal points. So these two focal points of an ellipse sort of define an ellipse. Indeed, an ellipse consists of all of the points which have the feature that the distance from them to one focal point plus the distance from them to the other focal point is always equal to a constant. And Kepler's first law is that when you have a planet orbiting a star, that star is always going to be at one of the focal points of that elliptical orbit. So this law gives us a kind of functional relationship which we can exploit to make this ontology log. So I would propose that this type here, an elliptical orbit around a star, is the co-product of this type here and this type here, this being an elliptical orbit with a star at its right focal point and an elliptical orbit with a star at its left focal point. Now, what do I mean by the left and right focal point? Well, here's my idea how you could define it. You could say I'm either looking above the galactic plane or below the galactic plane at this star, at this planet orbiting this star in such a way that it seems to be orbiting clockwise. And then you can orient your view so that this elliptical orbit has one focal point on the left and one focal point on the right. So you could say that this type here is the co-product of this and this. You can see my last video, Category for Beginners Everyday Language, where I talk more about how co-products can enter these ontology logs. Anyway, so if we say this, if we buy this, that this is either this or this, then all we have to do is define these things. And these are much easier to define using functional kind of relationships. So what's an elliptical orbit with a star at its right focal point? Well, I would say that it's the pullback of this diagram here. So we have an elliptical orbit which has a right focal point, that's a point in space, and a star has a centre, which is a point in space. So I think if you take the pullback of this part of the diagram, you get this notion. So what do I mean? Well, I'm really saying that this is the set of pairs of an elliptical orbit paired with a star, such that the right focal point of that elliptical orbit is the centre of mass of the star, okay? So you can see that this kind of makes sense by checking that this diagram does commute. So if we have an elliptical orbit with a star at its right focal point, so then that has an elliptical orbit which has a right focal point, and that should be the same point in space that we get if we take the star from here and find its centre of mass. So we can really define this as the pullback of this part of the diagram here, and we could define this similarly by a pullback. So you can see that these ontology logs can get fairly large, and I think using computers to represent them is a really good way to go. Another kind of general comment I have is, you know, sometimes when people see these ontology logs, they say, well, isn't that more complicated? I mean, wouldn't it just be simpler just to say a planet is a celestial body which has an elliptical orbit around a star, and just leave it at that, just make that English statement and leave it there? Maybe, but I mean, the trouble with sort of general statements in English and things is, you know, it's not always clear what they mean. I mean, that's one of the reasons I think it's kind of difficult to make these ontology logs sometimes, because when you look at concepts, often it's not really 100% clear, you know, what they mean and what kind of data could substantiate them. So personally, I actually find these ontology logs, once they're written out, are much kind of easier to understand than, you know, a lot of everyday language, because with everyday language, often it's not really clear what people mean, and you don't have these kind of potential databases to back things up. I mean, the benefit of these ontology logs is that you can look at a part of it, for example, a star has a centre, which is a point in space, and you can really think of this in a kind of very visual way, or a very sort of data-centric way. I mean, astronomers have databases of lots of stars and where in space those stars are. So this arrow here is not merely a kind of linguistic connection. It represents a kind of record which exists and documents this kind of relationship. I just want to say something else as well, and that's about what kind of context we can take these kind of ontology logs in. So, for example, in an ontology log, I may write a man lives in a house. Now, as a kind of global statement, this is very suspicious, right? Because not all men live in houses. Some men don't live in houses. They live in boats, or they're homeless, or whatever. And, you know, there are other men that, you know, maybe they live in one house in the summer and another house in the winter. So it's not really clear in general that this is a functional relationship if I'm referring to the set of all men and the set of all houses, but maybe I'm not. Okay, so you can also construct ontology logs which are just using a particular database. So for example, you could have a company, and in that company, all the men who work in that company do live in a house. And if you're just referring to the sort of database, you know, maybe you have like a spreadsheet of the places where your different employees live or whatever, then, you know, maybe a statement like this would make sense. So The general idea in these ontology logs is that you have some kind of database, which is what your ontology log is about. I want to give you enough tools to be able to make ontology logs about any type of subject you're interested in. It's a very great thing to do because, number one, you get a whole new kind of appreciation for the subject because you'll see things in different ways, and it really makes you have to formulate things very precisely when you are making these ontology logs. And number two, when you do this, you really see all this kind of category theory machinery behind the scenes, which is sort of defining concepts. So it's very pleasant in that sense. It's a real learning experience. In order to be able to say what we want to say using these ontology logs, it's very useful if we can make some more connections with set theory, because there's lots of things that you can say using set theory. So one important idea from set theory is the idea of the intersection of two sets. So if you have a set A and a set B, then their intersection is going to be the set of all elements which are members of A and members of B. Okay, so normally we write this as A cap B. And so it turns out that we can express the intersection of two sets using this notion of a pullback. So let's say we have two sets A and B, and they're both subsets of another set that we call C. When we're doing this in terms of everyday language, we could just make a suitably general set that it contains both of those. So let's say we wanted to talk about a female mathematician. Well, then we'd maybe have A as the set of mathematicians and B as the set of females, and they all belong to the set of people. So the set of people would be sufficiently large, or, you know, in other contexts, we could use the set of all things. That's a big enough set, I suppose. Anyhow, the point is that we can define this intersection of A and B in terms of a pullback. Okay, so it would be a pullback that looks something like this, a pullback of this part of the diagram. So if we have this part of the diagram which says a member of A is a member of C, and a member of B is a member of C, and then we just ask for the pullback of that, well, what's that going to be? So remember the definition of the pullback. This is going to be the set of all pairs with one element from here and one element from here, such that if we do this function on the first element, we get the same result as if we do this function on the second element. Okay, so if we want to be really precise about what this object means here in terms of pullbacks, we would say that this is the set of all pairs x comma y, with x in this set A and y in this set B, which is such that if we do this function on x, we get the same thing as if we do this function on y. But remember, these functions here don't change anything. So this is really the set of pairs x comma y, with x in A, y in B, and x equals y. So it's really the set of all, pairs x, where x simultaneously belongs to A and belongs to B. So I think it's pretty clear that this is going to be isomorphic to the intersection of these sets A and B. And so this kind of pullback idea allows us to be able to talk about the intersection of sets. So now I would like to tell you about pushouts. So pushouts are another very important idea from category theory, and for these ontology logs, pushouts are going to allow us to sort sets according to the values of functions, and they're also going to allow us to talk about the union of two sets. So in general, pushouts is a colimit of a functor which comes from an index category which looks like this. But I'm going to explain pushouts in much more simple terms, okay? So a pushout can be understood in this category of sets, and it's really the kind of dual idea to this notion of a pullback, which we've already seen many examples of. So I think the easiest way to explain what a pushout is simply to show you an example of one in action. Okay, so what I've got here, I've got the set of animals, or part of it. Actually, maybe you could call this a set of badly drawn pictures of animals, but anyway, here we have this set of names of animals, and we're sending these pictures to the names of the animals that they're supposed to be, and then we're also sending these pictures to a number of legs that they have. Okay, so we're sending this dog here to the number 4, this cat to the number 4, this ant here to the number 6. So this is really part of a kind of diagram. So we can think of this as a kind of part of this category set where we have this object, we have these 3 objects and these 2 arrows pointing out of this object here. So remember, in this category set, these objects here are sets and these arrows are functions. Okay, so what's going to be the push out of this diagram? Well, I think the easiest way for me to show you is just to construct it. So basically the way that we make a push out is that we take the discriminated union of these 2 sets, and then we identify things that have common pre-images. Now, I'll explain more what that means, but the easiest way is to just show you how this works. So firstly, let's take the discriminated union of these 2 sets. So normally when you take the discriminated union of 2 sets, what that means is that you tag the elements in one set with something, some kind of label, and you tag the elements of the other set with some different kind of label, and then you just stick those 2 sets together. Okay, so they have these different labels attached to the elements, so you can see which set they came from. Now, I don't really have to do this in this case because it's clear that these words here came from this set here, whereas these numbers here came from this set here. So that's the first step, is we take the discriminated union of these 2. The second step is to identify things that have a common pre-image. So what's a pre-image? Well, if we have some function from one set to another, and we have an element in the second set, then a pre-image of that under the function will be something that got sent to that thing under the function. So the pre-images of the number 4 in this case are this picture of a cat and this picture of a dog. Okay, so what we're going to do, we're going to look at what has common pre-images here. So this dog here has this pre-image, and this number 4 has this pre-image. So we're going to identify those 2 things. And so I use this squiggle here to denote that we're kind of identifying these things. We're going to kind of stick them together. Okay. Similarly, this cat here has this as a pre-image, and it's the same as this number 4. So these 2 things are going to be identified. And this ant here has this picture here as a pre-image, and so does this number 6. So we're going to identify those. Now, what we do next is just say that, so the way I like to think of this next step is that what we can say is that we've kind of drawn a network here. I mean, we can think of these as vertices. So we've got 5 vertices, and we can think of these green squiggles here as links. Now, what we can do is take the connected components of this network, the kind of separate pieces which don't have any paths between them, and each of those is going to become a kind of blob, a kind of element in this set that we're making. So this set's going to have two elements. This element here this element here and this element here. So we could call this pushout, which we've constructed, classes of animals with the same number of legs. So in this example it has two elements. This one here, which is sort of this one here, which represents dogs, cats and the number 4, and this element here which represents ants and the number 6. And then the other part of is these functions here, which kind of embed these sets here into where they belong. So we'd send dog, for example, to this kind of class which contains the dog, and would send ant here to this class here, and would also send number 6 to this class here. So we could call this function belongs to class. So a name of an animal belongs to a class, which is a class of animals with the same number of legs. So dog here belongs to this class of 4-legged animals. And also the number 4 labels this class of 4-legged animals. And the number 6 labels this class of 6-legged animals, which an ant gets sent to. So these pushouts allow us to talk about what happens when we sort objects according to particular features which they may have. Okay, so I've described how we can use pullbacks to represent the intersection of two sets. Now I want to tell you how to use pushouts to represent the union of two sets. So let's say we have two sets, A and B, and let's say they're both subsets of some larger set, C, okay? So in this case, I'm talking about colours. So we're imagining that there are two people, Alice and Bob, and they're wearing various colours. And so let's suppose that Alice is wearing red, blue and green, and Bob is wearing red and yellow. So our task is to find the union of these two sets and to describe it in terms of category theory. Okay, now we know how to take the coproduct of sets, but that's the disjoint union. If we took the coproduct of these two sets, we just take these sets, we'd take this set, tag the elements with something, take this set, tag the elements with something else, and glue those two sets together. The problem with that is that we'd be double counting, because we'd have a red tagged by one thing and a red tagged by something else. So there would be two members of the resulting set representing red. A little bit like if you counted how many points there were in this circle and counted how many points there were with this circle and added those numbers together, you would have double counted these points which are in the intersection of these two. So how do we find the union of this set A and this set B? Well, we simply take the push out of this diagram here. So these functions are just inclusion functions. And what I've got down here is essentially the intersection of A and B. So this is the colours which Alice is wearing and Bob is wearing, the common members of these sets A and B. So that just has one element, which is red. So let's just go through the construction of a push out here again. So the first step would be to take the discriminated union of this set here and this set here. So unlike in the last case, these two sets look kind of similar. So when we're taking the discriminated union, we better tag them differently. So I'll tag things that came from this set with a 0 and things that came from this set with a 1. Now, the next step in making one of these pushouts is to identify elements which have a common pre-image. So this red here and this red here have a common pre-image here. So we want to identify them. And we don't have to we don't identify anything else because nothing else has a common pre-image. So what we end up with is a set which has 4 elements. This element here, this element here, 3, 4 elements, okay? And you see what we've done, we've identified these 2 copies of red that we used to have in this discriminated union. And that's what we wanted to do because we've eliminated this double counting and we've really now got a set which is isomorphic to the union of this set. So we could label it to say a colour Alice or Bob is wearing. And we also then have these kind of inclusion functions here, these kind of is functions which just include these elements into this union. And so it makes sense to call this set A union B. So we often denote the union of 2 sets with a cup like this. Okay, so another important thing to be able to do in everyday language is to say that things don't exist. Okay, so how would we express, for example, that there are no 3-headed ducks? Well, one way to do it would be to say that the set of 3-headed ducks is an empty set. So we could write nothing to represent the empty set, the set with no elements. And then we could say a 3-headed duck is nothing. There's no functions going from a set which has elements to the empty set because there'd be nowhere to send the images of your members to. And so when we say that there's a function from this set here to this empty set, that could only mean that this itself is an empty set because the only thing that has a function, the only kind of sets that have a function into the empty set are themselves empty. So these must both be the empty set and this must be the identity function associated with the empty set. So another common thing that people like to do in language is they like to use this idea of the complements of sets. So they like, for example, if I say the set of all light switches in my house which are not on. So the way I could talk about that would be, for example, I could say, well, A is the set of all light switches in my house and B is the set of all light switches in my house which are on. So then I'd be talking about the complement of B with respect to A. So this would be this set of elements of A which are not in B. So how do we write such a complement? Well, it's normally written as A/B, where this looks a little bit like a minus sign because we're essentially kind of subtracting this set B from the set A. So this represents the set of elements of A which are not elements of B. So how could we speak about such a complement using our ontology logs? Well, one way to do it is to exploit this little theorem here, which says that X is going to be this complement, the set of members of A that are not in B, if and only if the intersection of X with B is empty and the union of X with B is A. Okay, so this is a very powerful result. It allows us to be able to talk about things being complements. For example, the set of light switches in my house which are not on. So the way that we can do this is that we can just make up a set called X, and then we can have a pullback which represents this set here, X intersection B, and then we can use this kind of device to represent that the object of that pullback is the empty set. So we just say, well, it's nothing is this thing, and that would mean that X intersection B is the empty set. and then we can form a kind of push out to represent this object here, X union B, and then we can say that that's equal to A. How do we say that two sets are equal using these ontology logs? Well, if we have a well-established kind of notation for representing these inclusion functions, like I'm using this word is, then the presence of inclusion functions going in both directions will mean that the two sets are equal. So we could make a statement like this in such a way. If you wanted to be a bit more sort of verbose about it, you could make a larger diagram and use those loops to represent commuting arrows, and then you could actually explicitly represent that two sets are isomorphic to each other.